Already introduced Juan on the left and myself on the right. We're going to take you through a breakdown of reinforcement learning with AI feedback, and we're going to hand out 4 of the best documented notebooks you have ever seen. And this presentation is going to be really packed with theory and hands-on implementation. So fasten your seatbelts and let's dive into it. Let's begin with training LLMs. Beyond using larger models and data sets for pre-training, the drastic increase in LLM quality over the past year or couple of years has been due to advancements in the alignment process, which is largely being fueled by fine-tuning techniques like supervised fine-tuning and reinforcement learning from human feedback. Human feedback, RLAIF is particularly a flexible and powerful network, and it allows us to directly fine-tune a model to align with complex human values and preferences. However, it comes with costs in resources and human labeling. Let's see these parts, let's brush through them. Unsupervised learning is about masked token prediction accuracy. This is what it's trained on. And even though it has good general text prediction accuracy, it fails in further generalization when it's for specialized domains, and also it fails in relevance when we're talking about context-aware responses. Further, supervised fine-tuning is also based on next token prediction accuracy. It is bridging the gap between from the pre-trained model. It is more specialized and context-aware, and it allows for enhanced consistency. So it ensures that the model provides more reliable outputs tailored to the problem at hand. More on this you can see by this post by our friend Raul and collaborator, who is explaining these things amazingly on LinkedIn. So both of these techniques are based on single token prediction accuracy. However, let's consider what makes a good text a good text. This is a question inherently hard to define, as it is subjective and context dependent. As known, even fine-tuned LLMs often hallucinate, respond with harmful or untruthful content, and they struggle with creative tasks or tasks without a ground truth, like summarization. Writing a loss function to capture these attributes is hard at least. For example, how would you calculate a metric to measure if the model's output is funny? Therefore, text generation cannot be judged slowly or improved solely based on the accuracy of the prediction of a single token. Wouldn't it be great if we could use feedback from like preference feedback as a measure of performance for the entire sequence? And that's the idea here. We're going to use methods from reinforcement learning to directly optimize a language model with human or AI feedback based on the entire token sequence. Let's dive into it and start from RLAIF to see the entire evolution. So in this schema, the AI model incorporates feedback during training directly from human labelers. In this way, it aligns itself with complex human values and tasks. Let's have a look in performance results for the task of summarization as published by OpenAI. The RLAIF model clearly outperforms not only the fine-tuned model, but also the reference summaries. So pretty incredible results. Despite its effectiveness, though, RLAIF requires a lot of human preference annotations to work well. For example, Llama 2 is trained using more than 1 million human preference annotations. This is 10 times as much as the data points used for the fine-tuning of Llama 2. With this in mind, we might wonder, is there any way to automate the creation of human preference labels for the reinforcement learning training? And that's why we're going to leverage AI to automate this collection. So the solution is AI feedback. Automate this procedure with AI feedback. New findings from Google suggest that reinforcement learning from AI feedback could be a viable alternative to reinforcement learning with high-quality human preference labels. Reinforcement learning for AI feedback utilizes an off-the-shelf language model to label preferences, eliminating completely the need for human intervention. This makes it a highly scalable approach compared to human feedback approach. A study published just 1 month ago by Google Research focused on summarization tasks. The two methods were found to deliver similar improvements. These promising results indicate that RLAIF has the potential to match the performance of the human feedback counterpart, providing a solution to scalability limitations and enhancing the efficiency of the LLM. In this graph, you see that human evaluators strongly prefer these two methods over the supervised fine-tuning baseline. The differences in win rates between the two reinforcement learning methods are not statistically significant. Additionally, when compared head-to-head, RL with AI feedback is equally preferred to RL with human feedback by the human evaluators, and this error has 95% confidence intervals. So we know that RLAIF is equal or better and more scalable than its human feedback counterpart. Let's see how it works. In this schema, the AI model incorporates feedback from another AI model rather than from humans. And here we raise to use what we call constitutional RLAIF. The constitutional framework was originally designed by Anthropic in order to overcome many of the shortcomings of RLAIF. Humans are involved here, actually. They are involved through providing the AI feedback model with a constitution. The constitution is written by the humans, and the constitution outlines the essential principles by which the model ought to make its judgments and its feedback, its preferences. To look how RLAIF works against constitutional RLAIF, there has been research by Anthropic on the task of a model being helpful, as originally it is by RLAIF, but also trained on harmlessness at the same time, which could change the performance of the model. So the plot shows the relative performance scores, and we see that AI is superior to human feedback from a performance perspective. The AI models maintain the helpfulness over the human feedback models, while simultaneously making improvements in terms of harmlessness. Also, what was noticed during this research is that the alignment of the labelers to the AI feedback increases with the bigger LLM size. So, approved. Last, about comparing these methods. Conversations about ethics are inherently subjective, but still, reinforcement learning from AI feedback is generally viewed to be ethically superior to human feedback for two main reasons. First, or three main reasons actually. First, it's much less subjective, given that the AI assistant's behavior is not dependent only on a small pool of humans and their particular preferences, but instead it's dependent on the AI and the constitution. So constitutional AI uses an explicit set of principles that determine the characteristics of the desirable response. Such an explicit set of principles can be created through a democratic process. For example, many more people can be involved in the conversation around these principles and around how models should behave and dictate this behavior through building up a constitution. Third, the AI, it can be ChatGPT that is applied to give the feedback, encompasses cumulative knowledge and bias from the entire internet. So that is much less bias than 20 labelers or 50 labelers. Let's now, after we did all the relative comparisons between the two methods, let's now see how reinforcement learning pieces together in a general picture with AI or human feedback. So let's start from RL. RL is a type of machine learning where an agent learns to behave in an environment by trial and error. The agent receives rewards for taking actions that lead to desired outcomes and receives penalties for taking actions that lead to undesired outcomes. The agent wants to maximize its reward, so over time, it learns to take the desired actions over the undesired ones. Now, how are these things pieced together, RL, LLM, and feedback? Let's start. The agent is the large language model. It's the trained model in this paradigm. We feed it with a prompt, which signifies a new state. The agent takes an action based on this prompt, and the action is the completion of the entire sequence of text. So we have a new environment that includes both the prompt and the completion. This we feed into the reward model, which rewards our agent depending if this is a desired action or not. So this is exactly when feedback comes in. In the previous session, we saw how human feedback was coming in here. What we're going to see now is how AI feedback is used to fine-tune this reward model in order to provide rewards that lead to desirable actions that are along to the constitution that we discussed, or actions that are aligned with complex human tasks like summarization. So this has been an outlook of how LLM training pieces together with RL and AI feedback. Next, it's time to dive into the real training pipeline. So get ready for more graphs. The training pipeline for RLAIF. You will be right to wonder what is going on here. And let's better start with the key piece of this graph, which is the reward model, aligned to the constitutional AI feedback. Let's see how this pieces together with our LLM model. Let's start from the beginning. The first main component for this graph and this pipeline is the LLM model which we want to train. The second main component is the reward model, which incorporates the feedback, the AI feedback. The first step now is to feed a prompt to the LLM and get a response. Then we feed the entire sequence of prompt and response to the reward model. And here we make a temporary stop along our pipeline. The reward model, as you can see, provides a scalar reward, and we make the stop here. The first goal is to calibrate the reward model to take a sequence of text, and then based on the AI preferences aligned to the constitution, it will return a scalar reward, which should numerically represent the AI preference. To fine-tune the reward model, we first need to create a data set of ranked responses. Let's move on to that to see how it's done. In this data set, each data point is consisted of a prompt and two responses. These two responses are generated by our LLM, as shown before. they are ranked by the AI agent into two columns, chosen and rejected. Let's zoom in how this ranking process is done. We start with sampling a prompt from a predefined dataset. Pass the prompt through the LLM model to generate two responses, left and right. Rank these two responses into chosen and rejected using the AI model as a feedback agent. And the ranking is determined with reference to the constitution that outlines the principles by which one response should be preferred over another. Now we have the AI ranked dataset, reference dataset, and it's used to train the reward model. The reward model scores each response with a scalar, as we mentioned. With fine-tuning, it learns to assign high scores to the chosen summaries and lower scores to the rejected summaries of this dataset. The trained reward model will eventually be used as a reward signal during the RL training process. An encoder architecture is preferred to be used as the reward model, and with a size similar to our original LLM. So, without further ado, now Juan, we've been through the entire process, and maybe before we go to notebooks, you have some questions, because Juan is waiting after your questions to explain the notebooks. They're really well made and go into some programming. So please, if you have any questions on this process, I know it has been a lot. I see in the chat. So both of the two responses are generated by our LLM. Yes, indeed, both the responses are generated by the same LLM. Sorry, this one. Our LLM is a fine-tuned language model.
Exactly. Remember that we want to take a model which we have previously fine-tuned, and we want to improve that model to comply with certain guidelines that we as humans would prefer. So the initial data set is, as we will see, is actually created by the base model, correct?
So next question is, how do we factor in biasness of LLM models for feedback?
So as Pano was explaining before, as we all know, LLMs are trained with data from the internet, which includes the bias of every person that has written anything on the internet. So it's a collection of biases versus human feedback that it also contains biases of the people that are actually doing the qualification of each argument. It's more limited in a way, because when you are doing RLAIF, you are working with probably 1,000 or a few thousand humans, versus when you work with an LLM to produce the data set, you're working with the compendium, the whole internet providing the feedback. So there's bias, but then there's constitution, as we will see also in the code, that tries to limit the bias and tries to drive or steer the model towards answers or towards picking the option that best aligns with humans.
Exactly. And don't forget that we also have a constitution on the side that can help align even better. Even when you tell to ChatGPT, you give it some instructions to be less toxic, for example, it actually has some self-critique and it can apply these principles. So let's see another question, which is, can you again share the results, the two results? So these results are for helpfulness and harmlessness when a model is aligned for both these tasks with RLAIF, and when the same model is aligned for these two tasks or values with RLAIF. And you can also speak up if you have questions. Not everything needs to come in the chat.
Yeah, I'm a bit surprised that RLAIF is doing better because we just give it a handful of examples, and so somehow it's beating human feedback, which is surprising.
Well, AIF can handle many more examples than human feedback because it's more scalable. And don't forget that if we use ChatGPT, which is already aligned to human feedback, and we use that for AIF, then we get even more alignment. So let's see another question. Do you have to add something more? Excuse me.
No, that makes sense. So essentially, they're using this Chat GPT model and doing on top of that. So essentially, it's an adding and one more extra step.
Yeah. Of course, you can use other models. We're going to see something later about this. So thank you for the question. Let's see the next one. The performance improvement here is about how much the model follows the Constitution. No, these are benchmarks that are actually measuring how good the model performs. Like here, how helpful the model has been to some questions. It's not about how much it aligns with Constitution, but it's more about how much the Constitution helps the model to produce better results. It still is like typical benchmarks that you can find also probably on LFR AI. This is from Anthropic. So the link is here to look in for more, how this was done. That was the reply to G and Jai. Sorry if I butchered the name. So then, Christos, what are some guidelines to ensure the AI feedback is similar or better than what a human would provide? Maybe Juan, do you have a reply for this question? Can you add something?
Well, I will not say that it necessarily is better. It could be better. The main thing about AIF is that it's scalable. In other words, you can have so many humans doing labeling, so many humans doing classification, but if you want to fine-tune a model aligned to humans, then the bigger the data set, the better, and a good data set. And as we know, an LLM like GPT-4 is a very good proxy of that. So by generating a database or a data set with a model like GPT-4, we are approaching very well what humans would do at a very lower cost, speed, and resources. So we expect to have similar results from the AI, maybe sometimes better, who knows? That's probably very, very much, a case-by-case situation, but at least it's going to be a more scalable solution. Of course, you don't want to qualify your data set with a low-level LLM. You want to use a high-profile LLM that already comes with a lot of knowledge and a lot of alignment with humans.
Awesome, Juan. So, Christos, if you have anything to add, I'm going to go to the next two questions, and then we can go to the notebooks. So, the next two questions are a bit from after the notebooks. We can answer them better, but let's cover them shortly. Proximal policy optimization is a better fit because it's the most proven, stable online reinforcement learning method that we currently have. It passes most of the benchmarks, and the stability of the method is the main attribute that we need here, and also the bootstrapping it does, so that our model optimizes, but doesn't optimize too much. So it optimizes in a controlled manner. And the next question is, are there cases where instead of using a reward, can we train the pre-trained reward model on the human feedback directly? Dino, or you're stepping ahead to further down this presentation. The answer is yes. For until we reach there, it's at the end of the presentation. For now, we're going to use AIF as used by Anthropic for preference ranking. So not directly as implicit signal, but to rank preferences instead of scoring directly. So now I think we are at the time that Juan can show many notebooks. You can pick up, Juan. I will stop sharing my screen.
Thank you very much, Pano. Okay, let's jump into notebooks time. We are going to be seeing 4 notebooks today. And let me tell you what are they about. The first notebook is going to get us started with a basic data set. We are going to start here with a base model that we had previously fine-tuned for human feedback, with human feedback in our previous workshop. So it's a model that is already advanced, if you will. This is going to be a T5, and this T5 originally started from the default or the base T5 from Hugging Face, and we took it through a whole process of human feedback some 3 weeks ago. We invite you to look at that YouTube video so that you can see how we did it. And you will see that between that process, yeah. Go ahead.
Can you zoom in a bit to the code, please?
Sure, absolutely. Is it looking better now? Or is not zooming in?
Great.
How about now?
Yeah, it's perfect. Sorry to interrupt.
Good.
Please go
No,
on.
that's fine. So in this first notebook, we will create a data set. As Pano was explaining, we first create the data set with the base model. In the second notebook, we will pass that data set through GPT 3.5 Turbo to create the aligned data set, if you will. Then we will take this new data set and we'll train the rewards model, which can also be called the preference model. And finally, after another presentation by Pano, we will do the actual PPO training. So let's get at start with dataset with the notebook number 1. And let me pass through this. This is a very simple notebook. We're going to import some libraries. And the main thing here is that we will take the base model that we will eventually want to fine-tune or improve, align. And in this case, as I said, is already a base model that we aligned with human preferences. And we will create a data set with this model, which is already pre-trained. For that, we will take this model. Let me run this cell. And let's see what is it doing right now. We are taking a data set that I will show you in a second. It's from Reddit. And in this one, we are asking the model to summarize one of these Reddits. And it starts with this big passage from Reddit and produces a certain summary. So the system is working fine. We are going to prepare this T5 model for generation. Since we trained it originally with LoRa, we are going to have to instantiate the LoRa configuration and create it as or instantiate it as a PEFT model. Next, we're going to load a data set from Hugging Face, and I want to show you what this data set is about. Let me jump here real quick. We will be working with the Carper AI OpenAI summarized comparison. It has very good and robust data sets. We will take it from the train, which contains 92.5K rows. And this particular data set contains 3 columns: a prompt, a chosen, and a rejected. And it is important to check out that this is the structure that is required by the libraries that we're using to generate the rewards model and to generate the optimization. So we have a prompt, we have another feature called chosen, which is the chosen summary from this prompt. And then we have another feature called rejected, which is another summary, but has been rejected. We're going to start with this library or with this data set. And for our toy example, we will pick just 1,000 samples from it. We will basically load the trained data set. We will randomize it, pick 1,000 samples, and create our new data set. Next step is we're going to tokenize the data set. We're going to be creating remember, we're going to be creating from each one of these passages, we will take the passage, pass it through the T5 model, and ask the T5 model to generate 2 summaries. So in this generate summaries procedure, we will receive an example or a sample, a line of passage. We will iterate 2 times through it, and we will create 2 different summaries, changing a little bit the parameters of the generation. We're going to create summary number 1 and summary number 2. That's all we're doing here. We're going to give it some additional parameters for the generation, and we're going to run it and save it to Hugging Face. In this line here is packed with commands. We're going to be generating the summaries and creating a dictionary that is going to be our final data set. When we run this notebook, we will get a new data set. And this is our new data set. It's hosted here. Now, before we had prompt, chosen, rejected. Now we have prompt, summary 1, summary 2. And we want now to take this as our starting point for the new training of this base model. Again, we just took one of these passages from Reddit, created a summary number 1, created a summary number 2, and we are now with a whole new data set. In this case, only 1K rows for the exercise that we're following. Once we have these, we're going to jump now to the next notebook. And this is where the magic starts to happen. As Pano was explaining, we want AI to take this input and to decide which one is better. For this, you are going to take, in this case, GPT 3.5 Turbo, and you are going to create a prompt. You are going to pass to this prompt, the context of each call is going to be the passage, the summary 1, the summary 2, and your instruction. You can go with something like, hey, GPT, read this passage, and then read these 2 summaries and pick the best one. Or read this passage, read these 2 summaries, and pick the one that has less evil, or whatever you want. The main thing here, the message to you here is you are going to use an LLM and you are going to give it an instruction to pick one of the 2 summaries to be the chosen one. And the other one is going to be the rejected one. Remember, we want a data set that has 3 columns, prompt, chosen, rejected. And we are started with here at this point with a data set that has prompt, summary 1, summary 2. And between the 2 summaries, we have to have GPT or whatever LLM model that you use, pick the best one in your terms. So that is the main goal here. Now, Pano said something that is critical. He said constitutional. I just gave you an example and I showed you how you can input any context to your LLM. But what is the latest way of doing it is by creating a constitution. And I'm going to show you the constitution that we created. This is going to be our constitution. We're going to tell, or we are actually going to pass this in green, this constitution as part of the context. Okay, let me step back a little bit. When you create a constitution, like when a country creates a constitution or any company creates a constitution. When you create a constitution for your use case, you want to get it out of GPT-4, for instance, and you give it a prompt and ask it, please, GPT-4, help me create a constitution to train a model. And I want this constitution to follow these rules. And GPT will throw the constitution that will be your base, your context base, your initial part for this training. So it is important that you define your constitution depending on your use case so that it follows your guidelines, okay? So we come from AI feedback saying that we can use just any prompt to an advanced way of doing it, which is create a constitution, create the rules of engagement for the model to follow when picking summary 1 or summary 2. This is the constitution that we created. You will have this notebook, so let's not read it. It will take some time, but you will see that we have defined some rules of engagement, some principles that we expect the model to follow. And then we have a prompt. When we are going to take the summary 1, summary 2, and pass it through GPT 3.5 Turbo or GPT-4, if you want, then you expect GPT-4 to follow your instruction, your constitution, and pick the best of the two summaries. So here we have defined the constitution. Here we are going to, we're getting the data set that we created. I just show you prompt summary 1, summary 2. And here we're just showing examples of that data set. Here we're going to rank the summaries, and this is where we are calling the model. Let me skip this one for a second and show you that we are just basically going to go through all these samples, 1,000 samples that we picked, and we're going to apply rank summaries and create our new summaries data set. When we go to rank summaries, basically what we do is we create a prompt as we know it with GPT-4. We pass it the constitution, we pass it our prompt and instruction, we pass it summary 1, and we pass it summary 2. At the end of this, once we call OpenAI's chat completion, it will give us a response that says the best one is summary 1, or the best one is summary 2, or the chosen one is summary 1 or summary 2, and we pick that answer, which is a dictionary, chosen 1, 2, or 2, 1. And we rank it, chosen is 1 or 2, and rejected is the other one. And we return that. So at the end of this process, we get a new data set. And I will show you now the new data set. This is our newest data set. We are with a prompt, with a chosen, and with a rejected. You can ignore the rest of the features that we have in this data set are just a way to keep track of the usage of tokens and whatnot. You can use it or not, but the really important and interesting features that we have to take care of are the prompt, the chosen, and the rejected. Now let's go back here, and now that we have, GPT provided the provided the data set, we can move forward to train the rewards model. And do you want to say something here, Pano?
No, it was just I saw another screen passing by. Please go on.
Yeah, sure. Okay, so in the rewards model and as well as in the PPO, you will find that the notebooks are exactly the same that we used for human feedback, RL from human feedback. So let's go through these quickly. We're going to create again, this is interesting. There are a couple of things that are here interesting. Number one, you want to pick a model that is good for classification, meaning, as you know, the transformer architecture has two big parts, encoder, decoder. You want an encoder model. You want a model that can be used for classification. In this case, we're going to start with the GPT-2 for sequence classification, and we're going to get a tokenizer for this model. And this model will basically take the data set that we just created with GPT 3.5. And then we're going to pick the prompts of the chosen and the rejected, apply some constraints like max length, because as we can see, there are very large content there. We pick basically, we are going here to enumerate and create the data set with the chosen IDs and the rejected input IDs. This is basically preparation of your data set. And here comes the key number one of this fine-tuning, and is in the loss function. When you train or fine-tune any regular model, you basically take a function, a loss function that will compare the inference of the model against the ground truth, and you calculate a loss, right? Here in rewards model, the way to handle the loss is different. You are going to do, instead of doing one inference in the training cycle, which is the typical, you will do two inferences. You will do one inference for the chosen and one inference for the rejected. You will take the logits of these two inferences, subtract one from the other, output preferred minus output rejected, apply a softmax on that, and then a logit on that, a log on that. So the idea here is to maximize the distance between the chosen and the rejected as a number, which is the signal or the reward, if you will. So that's what we do here in the training loop. That's exactly what we do here. In this function, we are calculating the loss. In this one here, I'm sorry, we are getting the inference of the chosen prompt or the chosen text. And here we're running it for the rejected text. Remember, we have summary 1, summary 2, then chosen, rejected, and we are basically creating inference here. And for the loss, we are using the difference between these two, finding the mean and applying log sigmoid and finding the mean. So that is a very, very specific thing of the rewards model that you have to keep in mind when you build your own reward model, if you decide to do so. Or most probably you will be using the libraries from Hugging Face. But those that follow me in LinkedIn know that I prefer to do it from scratch. So we do the training here. And at the end, we will have a model that is capable of throwing rewards that will tell to the PPO process which one of the two are more aligned with the human. So at this point, we have trained the rewards model. And before we jump into the last notebook, I think that Pano has another interesting part of the theory to explain. So Pano, on to you.
Are we going in these three notebooks first and then to the last one, or should I present?
Yeah, go ahead. I went through the three notebooks and now I am going to the last one. So present and I will do the last one.
So first present. Okay. Let me pick up my presentation and share my screen.
I had a question. Can we ask it right now, or shall we wait till the end?
Yes. You can ask.
Okay, so it's a really nice code and a very great walkthrough of it. So one thing was for the loss function, why we did not, because it's basically a kind of a binary thing, right? Whether 1 is chosen or the 0 is chosen. So why we did not go for a BCE kind of a loss over here rather than, writing, let's say maximizing a distance or something like that?
Yeah, you could experiment with that. The one I showed you is the one that we found that Hugging Face uses, and it's probably the most used. But if you want to experiment with other reward model losses, you can do so. The point here is, and the main objective here is to get the maximum distance between the chosen and the rejected so that the signal is clear. So there is nothing written here. There is no definite answer. Everything is a matter of experimentation. But as I shared, this is probably the most common one used for this type of scenarios.
Got it. Thank you so much. Yeah.
Absolutely. Thank you for the question.
I have a question. So when we do this, do we expect the performance? What's the performance? I mean, like summarization performance on the benchmarks. Are we expected to, if we do this more, it can surpass, it can be better than GPT 3.5, right?
When you do this, remember, we are taking a T5 model, which is much smaller than a GPT 3.5. And we want that T5 model to improve the summarizations based on the Constitution. We're not telling, this is not about making better summaries. This is about making summaries that are aligned with your Constitution. Now, if in the Constitution you give it rules to improve the quality of the summary, maybe you will get that. But the main point here is you're taking a T5 model that you will be using probably locally, and we have the national alert right now for those that are in America, and those that are not, sorry, I didn't get it. Yeah, it will come. I guess everybody's getting it here in America. Today, you're sending a test of the national system of alerts. Let me.
Okay, maybe I can pick it up and do the
go
last
ahead.
part of the
Okay, go
presentation.
ahead.
Juan, while I'm presenting, please share the notebook links from our GitHub page so that everyone has them. And so this until now, what we've seen is actually this part of the entire pipeline. Juan showed very nicely how to train the reward model. And right now, our pipeline is at the point that we're feeding prompts to our LLM, which is going to be trained with RL. And we're getting a text. We're feeding the entire prompt and text and the response sequence to our reward model, and the reward model gives us a score, just a scalar, which is representative of the human preference, of the AI preferences and the constitution that we have injected into our reward model. Juan also explained we have a BERT encoder for the reward model and a T5 fine-tuned model for the LLM, which we're going to further fine-tune with RL. Now, the PPO comes in, the benchmark method for online reinforcement learning. We don't need to dive deep into the framework of PPO and how it works. For this implementation, let's look at it more as a black box. So what PPO does, as we showed earlier in the graph that we pieced together the reinforcement learning with the LLM and the feedback, the PPO here takes care of that loop, the agent, action, environment, and reward. So we are feeding to the PPO the reward, and the PPO makes sure to optimize, update the weights of our LLM. Now, what happens many times is that this can, if it's not bootstrapped, it can lead to bad results. What that means is that the model, the LLM model finds a way, let's step back. The LLM model finds a way to trick the reward model to give it high reward by just producing gibberish. Like the text that it's producing doesn't make sense, but it finds a way to trick the reward model. This is a typical thing that happens, typical failure of RL training, that you find a way to violate the laws of your environment and get more reward while it doesn't make any sense. So to bootstrap our model, we use our initial LLM as it was fine-tuned. These two LLMs are the same before the reinforcement learning process has started. But as this model is trained, it's going further and further away from its initial counterpart. Now, we don't want it to get too far away. So we are bringing in KL divergence. This is a kind of TRPO method for those who know reinforcement learning. And what it's going to do is it's going to act like a regularization method. So it compares the two outputs from our LLMs, and the more far away these two outputs are, the further away, the more penalty we get in our reward. So our reward will get minimized if these two models get too far from each other. And since our reward will be minimized, the PPO will not update the weights to maximize the return. That will be a penalty in the weights, in other words. This now, as you are seeing, we have reached actually the entire graph. We have broken down and reassembled it. And last thing to mention before the fourth notebook is that, as Juan has mentioned, we are using the TRL Hugging Face library for all of this training. It has some amazing tools for supervised fine-tuning, for reward modeling, reward model training, and the RL training. It's fully integrated with transformers, and you will find it really useful as you go through the notebooks. So it's time for the fourth notebook. Before we go to that, any questions for a couple of minutes that we can cover? Let me check the chat. Juan, can you hear me?
On it.
I'm having some problem with the chat. Maybe you can go for it.
Correct. Yeah, no, all is good. So
okay.
let's start with the fourth notebook here. We only have 5 minutes left. So I'm going to, this is a very well documented notebook. So I am sure that once you get it, I posted a link to download the notebooks in the chat. Please get it from there. You will see that it clearly explains everything, but I want to show you the key parts of this. Number one, we are going to be working with three models. The rewards model that we already trained based on the constitutional AI F that we got from the previous notebook. We will get a base model, which is the one that we eventually want to make improve, and then we will get a reference model. The reference model is basically a frozen copy of the base model. So let's see how that is instantiated. First, we go about getting the dependencies, some 1dB to keep track of the process. Here, I'm going to skip all this part. We're getting basically the rewards model that we already trained in the very previous notebook. We're getting a scoring function, which will take the two summaries produced by the base model, the chosen and the rejected, and we'll produce a score based on that. The score that we will take is taken from a logit and from a softmax, I'm sorry. We return also the logits, but we're going to be using the softmax as the scores to be passed to the PPO. We're showing you here an example of what it produces. As you can see, we're passing a summary, we're giving a chosen and a rejected, and it's providing a 0.52 on the chosen, 0.41 in the rejected, which is expected. There's going to be a difference between them, and the chosen is expected to be higher than the rejected. Second, and I'm going to approach the key parts of this, we are going to instantiate our T5 model, which is the base model, the policy model, the one that we want to optimize. We are going to instantiate this model. Again, I'm testing it here. It's working fine. We're going to fine-tune it with PEFT and LoRa. Again, if you have done this before, you will find this familiar. If not, this is a great opportunity to learn about fine-tuning with PEFT and LoRa. Just instantiated the model. And look at this thing here. I'm going to expand this model and see how these models, last component, last layer, is an LM head. This is a language model head, okay? This is fully an instantiation of the language model head. Let's configure the PEFT and LoRa, instantiated. Number of parameters to be trained is only 0.4% of the whole number of parameters. Now, we're going to instantiate the PPO model with a value head. This is important. You have to use a value head at the end of this model so that the PPO can work. I just showed you a model that ends with an LM head. This model ends with a value head. This is the LM head that we had in the previous model, But this instance of the same model ends with the value head. What is this? Is basically the values that the model is giving, and those are the ones taken by the PPO policy, by the optimizer, and to define what is the best way to train the weights of this model. So that's key here. That is the other thing that I wanted to show here. And third, we have to use a reference model. To do that, we basically create a reference model from the policy model, and this is going to be frozen. This model will not change. What will happen is that as we train with the scale divergency, we will be, or the system will be comparing the weights or the responses between the policy model that we are fine-tuning and the reference model, and make sure that the distance, the jumps are not too big, that are within a certain minimum proximal little jump. That's why the word proximal in the PPO. And that will also help us to avoid reward hacking. Then we're going to prepare the data set for the rewards model, for the training. Basically, we're taking again the initial data set that I showed you, the one with 90,000 and some records. This is going to be the one that we will use again for this training. We instantiate it, we shuffle it, we take a sample, we create the trained data set and the eval data set, and then we go to the boilerplates, tokenizers, etc. before we jump into this is hyperparameters. Sorry to go that fast because we have like 1 minute, but we jump here to the training loop. We're getting to the training loop here, and in the training loop, basically we are getting every one of the samples or the batches, passing it through the model, giving it to rewards model, creating the inference from the trainer, appending it to the tensor, and then
Juan,
eventually, yeah.
We have half more hour.
Oh, really? That's
yeah,
amazing.
You don't need to hurry.
Oh,
Just pass this loop. Yeah, no.
Yeah.
Pass this loop more slowly because it's really interesting, please.
Yeah. I thought they were until 2:30.
Yeah.
Amazing.
No.
Very good.
We have half an hour. People can go.
Okay, so let me summarize
then...
up to here. I have instantiated 3 models: the rewards model, the PPO model, and a reference model. And at that point, we're ready. We have created the boilerplates for the data set, and we're ready to run the training cycle. In this training loop, we're going to get the samples in batches, and for each batch, we're going to run inference. In the PPO trainer, we generate the inference of these summaries, and we append them in a tensor. After we go through all these all the samples in the batch, we are going to decode this into a batch response, and we're going to create the chosen summaries and the rejected summaries. These chosen summaries and rejected summaries will be then passed to the scoring system that we created above. Remember, we created a scoring summary function that receives the chosen batch and the rejected batch, passes that through the rewards model. Then, using softmax, it will calculate the rewards or the signal and return it to this training loop to actually fine-tune the next step on the policy model. So after we go through each one of the chosen summaries and rejected summaries in the scoring summaries function, we get the scores, and then once we have all the scores, we train, or we give a step in the PPO trainer, and with these stats we get the next step on the policy model. For each one of these steps, we're showing a series of statistics that will tell us how is the model behaving. So after the training, this is a long training, but actually it's 1,000 samples. Remember, we didn't do a huge thing for the sake of the exercise. We save the model and we test it. In the testing, loading the model, and we get the function that will generate summary. We pass it down here. We pass it a text, and we create an inference, and we get the summary of the trained model. Wow. I guess I should repeat the whole thing slower, Pano. But go ahead, Pano. Yeah, I thought we had until 2:30. I'm sorry about that.
But no worries. I mean, it's good for people to also go into breakout rooms and see all this stuff for themselves. So we should probably push them. Sarah can probably is up to it probably, and we will be going around the breakout rooms with Juan to check how you're doing, answer questions, and then we're coming back to the main room to answer a couple more questions, see one last slide, and close off. So Sarah, are you ready for breakout rooms?
We are ready. All right.
Okay.
Well, put everybody in the rooms right now.
Awesome. Let's launch. A dedicated AI model. We can use a dedicated AI model as a reward model. We don't need to train it. We can take it off the shelf. It's going to be used only for inference. And this is what we call implicit signal. So think about that. You have a chatbot and you want to get feedback on the responses. So you're doing a sentiment classification and you're using a Roberta classifier for sentiment classification to directly tell you in a binary classification if this is good or bad. You don't need to train a reward model for this. You can use Roberta directly as a classifier instead of the reward model and use the logics that Roberta outputs as the reward. That's what we call AI feedback with implicit signal. What we did until now was explicit signal. Also, what you can do, and me and Juan have already done this, it's in a notebook in the repo. You can use ChatGPT as a direct AI scoring model. Instead of using ChatGPT to rank your preference dataset, you can use it directly and ask it to, hey, output a score for this summary. And it gives you a 0.5 or a 0.8. Output a score from 0 to 1, depending on this consecution. You can still use the consecution method. So that's what I wanted to show. And any questions on that? We have 5 minutes to go. If you have more questions or feedback, please shoot. I'm going also to check the chat, but you can also just, Christo, you have a raised hand, please go.
Yeah, so question about using the Constitution for grading, on a scale of 1 to 0 or whatever it is. Is that something that you would just always want to have in the prompt, or are there ways, like with various APIs, to score different things like toxicity? I know with Ragas, there's ways to have multiple metrics and then use sort of a harmonic mean. Are there other methods to do evaluation like that for kind of in a constitutional way?
Amazing point. Yeah, you can use Ragas and pick one of the elements or all of the elements that Ragas outputs, those numbers, and use them as your reward. And this would be a great case for summarization. Probably you can, for summarization, you can use Rouge scores, right? You can evaluate summaries using the Rouge scores. This is a benchmark evaluation. So that's a very good point. And you can use anything that can take text and give you a number. It can be already up to the task, or you can train it to be up to the task. You can train it either directly on a data set of text and number, or you can train it as we did on a data set with 2 responses, rank them, and teach the model to output numbers that represent this ranking. This kind of preference scoring takes more time, but it's very robust, because even if you use ChatGPT, it's not a total expert in knowing what a good summarization is. It's a bit of a vague task. There is no good, completely correct answer. So using this preference and constantly optimizing and going better and better is a very robust approach for these tasks. The other one is what you mentioned, use the evaluation scores. It's also very robust. So great point. Thank you. I don't see, maybe not looking the entire chat. I don't see more hands or messages in the chat. So let's wait a couple of minutes for any more questions. And until if someone doesn't have a question, what I'm going to say is, sorry, I posted the wrong notebooks. The initial GitHub repo that Juan posted and I reposted is there. This is where you should pick up your notebooks from. I will repost them here. The names or RLAIF, RLAIF, all of this at some point became a bit confusing.
Hey, Pano, let me let me do a big recap of the entire thing. So, number one, we utilized 3 models: a rewards model, which was fine-tuned already with one of the data sets that we created. Then we have a base model, which is the policy model, the one that we want to align with human preferences, or in this case, with AI preferences. And this is going to be the core model that we aim to align. And during the RL process, this model will become the policy model, which drives the decisions and actions. And third, we have a reference model, which is a copy of the policy model and is frozen. And we use it to compare or to benchmark and monitor the evolution of the policy model through the reinforcement learning. In the training loop, which we went a little bit fast, but then recapped, we have 3 main steps. The first one is we generate the summaries that are derived from the policy model. We ask the policy model to generate a batch of summaries. Then we take this batch of summaries, the chosen and rejected, or the 2 types of summaries, and we pass it to the rewards model for an assignment of a reward. Then we receive back from the rewards model these scores that the reward model produces, and then we pass them to the model adjustment via PPO. And when we give it to the PPO, it refines the weights of the policy model by nudging them, adjusting them a little bit towards human preferences. And this is an iterative training loop that at the end we expect to bring the policy model closer to what we expect as humans. That's a big summary of what we saw today in the last notebook. I feel so ashamed by going so fast through it, so I wanted to give that recap.
And also we have a session already delivered for RLHF, where these 2 very important notebooks, the 3 and 4, number 3 and 4 are presented again by Juan. So we will post it here, and you can also have a look there. Sarah, do we have any feedback forms this time, or?
Nope, not for this
Okay,
session.
great. Okay. The recording link will be posted, and also we will post the YouTube video there for RLHF.
Yeah.
So I want to thank you all for attending and for going through this very packed stack with us. I hope it became a bit more clear. And thank you, Juan. Thank you, Sarah. Maybe you want to say something.
Yeah, thank you, Pano, and thank you, Sarah. You went through a 90-minute session of what took us over 2 months of learning. So thank you for hanging out. Watch the YouTube video once it is posted. Study the notebooks, and you will catch up very quickly. Get us on LinkedIn. We will be more than happy to answer any questions.